Hey guys, so today I'm going to be telling you about nuclear fission, and this video and the next one is going to be nuclear fission, the other fusion. Do not confuse the processes because they are kind of, I like to say is the other way around. What happens is not completely the opposite from each other, but in any case do not confuse the processes, okay? So nuclear fission occurs when a stable isotope is struck by a neutron. The isotope absorbs the neutron, becomes unstable because of the neutron, and splits apart. When this happens, they release a large amount of energy, okay? So this is not like radioactive decay, that something is already unstable and decays in order to become stable. This is something that I create. So I get an isotope that is stable, but I make it unstable by hitting with a neutron at high speeds, and then when it absorbs the neutron, it becomes unstable, splits apart, and releases the energy, okay? So unlike natural radioactive decay, fission is not a natural event. That's what I just told you now. The isotopes that undergo fission include uranium-235 and plutonium-239, and most nuclear reactors use uranium-235. If you are wondering what is this number 235, 239, that's the mass number, the number on the top when you see the chemical symbol, okay? So the number of neutrons plus protons. The fission of 1 kilogram of uranium-235 releases more energy than burning 2 million kilograms of coal. So what this means is, if I use nuclear fission in nuclear reactors, so if I use this as a way to generate electricity, then as you can see, I can generate a lot of energy from a smaller amount of fuel. So this is very good in terms of energy demands. Now there are downsides as well, which you already know if you saw my other videos on energy resources. This particular slide is not mine, it's from BoardWorks, okay? Now, nuclear fission. So this is the step-by-step process. Here it is. I have a large nuclei, okay? I have the neutron. It's going to collide. This neutron carries on moving. I get two smaller pieces that make up the bigger nucleus. And then two neutrons again leave, okay? So a neutron collides with a stable nucleus. It shouldn't say unstable in there. For example, a uranium nucleus. The uranium nucleus now becomes large and unstable, so it splits into two similar sized particles, or smaller nuclei actually. Neutrons are released, and these neutrons can collide with more uranium neutrons. And each of these neutrons can create another splitting, so it can create another event of nuclear fission. So because from one neutron alone I can have multiple nuclear fission processes, and they keep increasing every time I have one process to happen, this is called a chain reaction. So one can generate two, that can generate other two, and so on, okay? So in this slide, I mean, the information of course is important, but this should be a stable nucleus instead of unstable. And then because of the neutron becomes large, unstable, and it splits. I'm going to add this video for you to see a lab representation of nuclear fission. So they have lots of mouse traps, and they put golf balls or ping pong balls, I believe they are ping pong balls, on top of the mouse traps. And then they release one ping pong ball on top of all the other mouse traps. And as you can see, setting up one of the mouse traps sets up other mouse traps, and there you go. That's a representation of a chain reaction. So this is a representation of nuclear fission, for example, how it would work, or how it would look like if we could see it, okay? So in case you don't want to watch the video, although the video is much better than this animation, I have this animation from Footprint, so the animation is not mine, and it's showing the process. So again, I get one fission neutron that creates fission, and then they release other fission neutrons, and then they keep releasing other fission neutrons. This animation is not perfect because it does not show the original neutron carrying on, but this is for you to have an idea. So one fission event can set up other fission events, and therefore I have a chain reaction. So what isotopes am I going to use? I can use enriched uranium, which is uranium-238 or uranium-238-92 if you want to think about the mass and the atomic number, which is non-fissionable, and I can use uranium-235 or uranium-235-92, which is fissionable, okay? Now, I use this in power stations, okay? So the uranium-235, I don't have to do anything. But the uranium-238 changes into plutonium-239, or then if you would like to have the mass and the atomic number, plutonium-239-94, which is fissionable. So you can get these isotopes to generate enough energy, which you're going to use to generate electricity in a nuclear power station. You do need to know the isotopes that you use, okay? So, all these keywords in here are necessary for you to explain nuclear fission. And why is nuclear fission going to be useful? So the link that I have in there is going to set up or get you to a page where you have 3 different videos that you can watch, okay? They are called the activities in the BBC bite size. And you can figure out why nuclear fission is useful. But as I already told you, nuclear fission generates a lot more electricity than the same amount of fuel with other energy resources, coal, oil, for example, gas. So it's going to be extremely important to help us meet the demands. So the amount of energy and electricity that we need on an everyday basis, okay? So it is useful, okay? But on the other hand, you need to be careful with something else. So I'll go there. So when I use nuclear fission in a power station, how does it work? I have a nuclear reactor, a boiler, a turbine, a generator, and the generator connects to the national grid. So this part of the boiler, turbine, generator, and national grid, you should already be familiar with them, because that's the same that works in a coal or oil power station. There are a couple of features that are new, so we are going to figure out how this works. This particular PowerPoint, or slide, sorry, this particular slide is as well from BoardWorks. So, first, I get in the reactor nuclear fission in the uranium fuel rods, releasing heat which is used to boil water, okay? So I boil the water using a coolant fluid that is going to pass through in tubes within the part where I have the boiler, and the water is going to boil, okay? And this is because this liquid is super hot because of the nuclear reactor, so it got heated up due to the nuclear fission events. Step number 2, the steam is going to go into the turbines and is going to make the turbines to spin, okay? And this is because of the high pressure that the steam has. Then, next step, the turbine is connected to a generator. So as the turbine spins, the generator spins. The generator, as the name says, generates electricity using electromagnetism, so something that you're going to learn later on in your videos. So when the generator turns, electricity is produced, okay? This electricity is going to go to the national grid, to the computers, and for me to try to make this process more efficient, I'm going to use the steam that doesn't have high pressure anymore, so it's not helping the turbine to move anymore. I use the steam to go up to the cooling towers, where the steam is going to be cooled down and condensed back into the water, and then they go down from the cooling towers into the boiler again, so it can be reused, okay? So this allows my process to be overall more efficient. So this is how it works, a nuclear power station. So in summary, if you want to take notes, this is what happens. I have my reactor, which has the fuel rods where fission takes place, and it has these control rods, which are made of boron, that absorbs neutron. These rods are extremely important, and I'll tell you why in the next slide, I believe. So I have the reactor. When nuclear fission takes place, the coolant, the fluids, is pumped through the reactor, okay? And the coolant is going to make that the fuel rods, as they heat it up, the coolant is going to go into the part where the boiler is, where the water is. So the water in the boil is turned into steam. The steam is going to go into the turbines, so makes the turbines spin, which makes the generator spin, and the generator generates electricity, which is going to be transferred to all the country through the national grid. So this is, in a way that you can take notes step by step, how the nuclear reactor works. Now, as I told you before, it works just like a coal power station or an oil power station. However, the way that I generate enough heat to boil the water is different. Here is by using nuclear reactions, so nuclear fission. So I have the fuel rods, but I need these boron control rods. They are extremely important. So this is what happens. These are the boron control rods, okay? And when they are down, they absorb any neutrons they are going around, okay? If I decide to take him out and put the fission tubes, or the fission, I cannot remember the name now, but if I put the fission tube, so the place where I have my fuels, if I put them in, then fission takes place. Now, if you remember, there was this huge disaster in Ukraine, in Chernobyl, where a nuclear reactor overheated and exploded, which sent radioactive materials and radiation across cities and countries, really. So, because nuclear fission produces a chain reaction, if there is no way for me to control this chain reaction, the reaction can get out of control. Each fission event produces a lot of heat. So therefore, if I cannot control the amount of heat, I can risk my reactor to explode. So this is what happened in Chernobyl. They actually had the boron control rods, but on that day they were making tests and they shut them down. So because they shut them down, the boron control rods could not control the nuclear reactions happening in the nuclear, well, the fission reactions happening in a nuclear reactor, and therefore the reactor overheated and exploded. So this is for you to understand how important it is that I have the boron control rods. So these are the fission rods, which before I couldn't remember the name, and these are the boron control rods. So when they are out, I have fission happening. When they are in, fission cannot happen, or I slow down the process of fission because I'm absorbing neutrons. So this is why they are in, and they are extremely important, okay? This slide as well, this animation, is from Footprint Science, so it's not mine. Alright, so I told you everything you had to know, so this is not working. I told you everything you had to know about nuclear fission. I'm just going to finalize by giving you an exercise where I'm asking you to write down the steps for generating electricity in a nuclear power station using all the words that I have in here. And you can read the words, so radioactive, turbines, uranium, released, atom, steam, unstable, nuclear fission, fuel, coolant, energy, electricity, transferred, plutonium, and generator. So try to make a paragraph with all these words. I'm going to move on, so pause the video if you want to try, and the model answer is going to show now, okay? So, the fuel in a nuclear power station is uranium and plutonium. These are radioactive. The nucleus of an uranium or plutonium atom is unstable and easily splits into two. Again, I should have said unstable once it gets hit by the neutron, okay? This process is called nuclear fission. A lot of energy and heat is released in this reaction. This energy is transferred by a fluid called the coolant. The coolant gets very hot when it leaves the core, the nuclear core. This energy is used to turn the water into steam in the heat exchanger. The steam drives the turbines, and the turbines drive the generators that generate electricity. So this is an example on how you can explain the whole nuclear fission. I actually could have put something to do with the chain reactions and the boron control rods. So say that this could set up a chain reaction or sets up a chain reaction, and boron control rods, which absorb neutrons, can be used to slow down the fission process or the fission reaction. But anyway, this is all that you need to know about fission. In terms of fission and the radioactive waste products that you get from fission, go on the videos earlier on the GCSE revision, so the videos that are to do with energy resources, because I have more detail about what happens after you generated the energy with fission, okay? This particular video is more about how fission happens. So up to my next video, be happy and healthy. Bye!